Okay, I guess we can get going. So welcome to Markov Processes and to your new semester. My name is Jem Corcoran, and you should just call me Jem. And I finally got the Canvas page up, but I just, sorry, I'm getting distracted reading chats already. If you got an email from me, you'll know that I had a lot of problems with dead links, and I just found one 5 minutes ago that I fixed, which is probably the one you care about, which is the syllabus. So I want to just look at the Canvas site with you for a moment. Not there. Here we go. Okay. Thomas Neal, just because I can see you because you're in a box, thumbs up if you could see my screen. Okay, awesome. So here is the course Canvas page, which is finally up and going. And I just wanted to point out a few important things here. So up here, there's just going to be course announcements. I assume you guys get pinged on that stuff. I don't know what your settings are. I think it depends on your settings for Canvas. So let's move on down. Here I have a link for an article from American Scientist that you do not have to read, but I think is really cool and awesome. So Markov chains, which I have to define today for you, were created by a Russian mathematician named Andrei Markov, and he lived from 1856 to 1922. Although I don't know exactly when in his life he came up with Markov chains, and I doubt he called them Markov chains. But he came up with them in response to, well, what he was trying to do was analyze occurrences of words in poetry. And this article is about that. It's kind of fun, talking about occurrences of words in poetry and how Markov got started. So totally optional reading. Okay, so the banner is not just a random picture. It was put in here because a big part of this course is going to be about queuing models, which is people lining up to servers and having various routing probabilities and probabilities of coming back around and different service times. So that's there because of the queues that we're going to study. Okay, so down here is a button that says start here, ignore it, because it's just going to say, go read the syllabus. And before I go over the other buttons, I just wanted to look at these reddish buttons here. So this is a Zoom link to the course, and this is a Zoom link to my 3 office hours. Now we have 2 TAs, and they're going to be establishing office hours over the weekend, so you'll know them by next week. So you should be able to get a lot of help in this course. But one secret I want to let you know is that all 4 of these links are exactly the same. So it's all one Zoom session. So if you just store that somewhere, you'll have an easy time getting to class and office hours. Okay, so on the syllabus page, which was not visible a few minutes ago, that's a sketch of Markov. And actually, this picture in the middle came from that article. So I have some basic information. My office doesn't really matter at this point because no one's there. Office hours, sorry, right before class, I realized they were wrong, but they are on the front page on those buttons, and I will fill them in here. These are our 2 TAs, Richie and Kayvon, and their hours are to be determined. But like I said, there's going to be a lot of opportunity for you to get help here from myself as well. So I'm not pushing you off onto TAs at all. I am here for you. And so is Gomer. Ugh. In case you were late to class. Not late. This is Gomer. He is here for you as well. Okay, so there's no book, as you've noticed. And the reason is because I just can't bring myself to stick to a book, and then people will get upset that they bought a book or something, although everyone bootlegs them now. So what is coming out in this class is, I don't want to take the time. All right, I'll do it. Go back to the main page. I just recently, like 3 days ago, decided to put together, see this blue button, evolving course notes. And because I spent all my time in the last 2 days writing a whole prerequisite chapter, I'm not up to date on that yet for stuff we're going to talk about next week, but I will get that up to date this weekend, and I will try to stay way ahead of you. So back to the syllabus. In here, there is a topic list. Some things we're going to do, at least this stuff, and maybe some other stuff. And I talked to a bunch of you in those little meetings I had to find out what kind of applications you wanted to see. And if I didn't talk to you or you can think of something that you want to see Markov chains applied to, let me know. Okay, so down here, there's this line which has a quote unquote paper syllabus. It's not on paper, but if we were in a class, this would be something I would hand out. And it actually has a little more information, which is exam dates and homework policies and things like that. I won't drag you through that. You can read it at your leisure. But I do want to point out that the exams are on Thursday evenings. And so you should, and the reason is I want to give you more time to take them. So they are designed to be 50-minute exams, but I'm giving you 2.5 hours, and you could even come late and you might be gone after a half an hour. So I want to make sure there's no big time crunch there. And so check out, oh, sorry. And in addition to that, if I'm taking your Thursday evenings, I'm giving you back the next Friday. Well, there'll be no class the next day. So check that out. Try to clear your calendar if you can, but if not, let me know as soon as possible and we'll work something out. And then for those of you that really want a book, these are 2 books here, and these links are directly to PDF, so you don't have to buy them. These are 2 books that I've used to teach the course in the past. This one down here by Taylor and Carlin is a little bit on the low end, and this one by Richard Durrett is a little bit on the high end. And we're going to be in between them, closer to Durrett, but I also think Durrett's is not friendly to read, so that's why I didn't make it a requirement.
Hey, Jem.
Yeah.
It's Richie Clancy. I'm one of the
Hey.
teachers of the class. If anybody is interested in getting a paper copy of the book, they can get it for $25 through my Springer, the CU library. If you need more details, they can email me or I'll post something to Canvas.
Awesome. Is that for Durrett?
Yeah, correct. They're essentially stochastic
Yeah.
process. Yeah.
Awesome. Okay, what else do you need to know? So again, make sure you check out the paper syllabus here. I'm going to put a link on the front page to make this more prominent, but that has important information about homeworks, and there's going to be a couple of dropped homeworks, and this is supposed to be, I usually drop 1, and now I'm dropping 2, and it's supposed to be helping you in this stressful pandemic. So it doesn't really seem like that much of a help. But one thing I've tried to do since the pandemic has started is be incredibly flexible. But with a class this size, it's not really fair to my graders for homework to be coming in at all sorts of time. It's like really a nightmare of logistics if they come in late. So we have at least 2 drops, and I am not promising anything, but I usually surprise people at the end with an extra drop. And now you think that's coming, and I've just ruined that. But that would be 2 drops out of 10. And of course, if something comes up that's really serious, like you do get COVID, or you have a relative that's really sick, or just let me know and we'll work something out. Okay, back to the front page. Please let me know if you find more dead links in here as well. Here is a tab, oops, sorry, lectures and videos. And at least before class, if not even earlier, I'm going to have a module up that corresponds to the class. So today is module 1, and this is the date that it goes with. And if you click on this, you will see that my internet is really slow. You will see that what we're going to do, kind of overview and objectives, specific things you're going to learn. And you'll notice that as the semester goes on, these will get worse and worse. Like this says, define a stochastic process, and in particular, a Markov process. But as the semester goes on, I'll be rushing and just write stochastic process. No, I'll try not to do that, but usually that happens. So down here is whatever you could read. None of this is required reading. You should be able to get all the information you need completely out of the lecture. But the course notes that I'm starting and posting have a chapter 1 up, which is all kinds of background material, but I don't think it's all important background material. I think what's important is I included it for completeness, but I think what's important is section 1.6 and section 1.9. And section 1.6 is about the important distributions that we need in this course. You probably have heard of the normal distribution, the exponential, whatever. We're actually not going to need a normal distribution in this course, but I have some lists for you of what we will need, and you can review them there. And then after the course, I'm recording this lecture, and I will sift through it real quick for privacy, so that, if you don't want to, I'm not going to assume anyone wants to appear or be heard on the video. So I'll and I think at least 10% of you are in the witness protection program from what I've heard. So I will be blacking out some stuff in the video, but I will get that up the same day. And you would find an assignment down here. Okay, I think that's all we need to do. And this tab over here is a generic tab that goes on every Canvas page about resources from the university. Okay, any questions on anything procedural before we get started? One that I think I can head off, programming. So there's some simulation in this course, and it's not going to be a huge part of this. And in fact, sometimes I will give you the option on a homework assignment. You can code up this, or you can do this theoretical problem. So you can kind of choose what you like. And you can code in anything you want, but for the purpose of illustration in the class, I'm going to be using R, which is not something that I think is great for Markov chain simulation, because it's usually really grindy and it would be slow in R, but I think it's perfect for just teaching it. But if you want to use Python or anything else, Julia, whatever you want is fine. And if you don't know any coding or have any preferred software, I will put up mini tutorials in R as we get into that stuff. Okay, now, do you have any questions? And meanwhile, I'm going to try to share my tablet screen, because this always takes a moment. So, okay, so the important distributions for this course that you can find in section 1.6 of the notes that I've posted are these 4 for the discrete distributions, and these 3 for continuous distributions. So Bernoulli, binomial, Poisson, geometric, and then the continuous side, uniform, exponential, and gamma. And probably you've all heard of these already. I would check out 1.6 anyway to make sure we're on the same page in terms of notation. And also, because I don't like my courses to depend too much on prior knowledge, when we first talk about each one of these, I will probably do a little introduction to each distribution, small. Okay, so I think we're ready to go. So here's a statement that's going to scare you, because it's going to make you groan and wonder why you're here. But got to start somewhere. So a random variable is a mapping from an experiment involving probability and randomness to the real numbers. And so a simple example would be to define a random variable x. So I'm going to do a coin flipping experiment, and I'm going to let the random variable be 1 if I get heads on the coin and 0 if I get tails. By the way, Richie, I didn't mean to make you stuck here. If you were just checking in, you don't have to stick around for the chat.
I figured I might learn something if I stuck around, so thank you.
So here's our experiment with randomness involving probability, the coin flipping, and then the random variable takes the outcomes of that experiment and gives you real numbers. And this is obviously a discrete random variable. And that's really all I want to say about that. We're not going too far into the review. But for continuous random variables, you know what? We don't need that yet. So let's just do some Markov. By the way, all of that stuff is in chapter 1. So a Markov process is a certain kind of stochastic process. And I want to define that for you. So the word stochastic means random. And the word process means something that's evolving through time. So a stochastic process is just a time-indexed collection of random variables. That's not going to fit. Time-indexed collection of random variables. It's the last time you'll see me write these 2 words. It will be RV from now on. Thought it would be in poor taste to start my first definition with abbreviations. Okay, so before I tell you what a Markov process is, which is a specific kind of stochastic process, I did want to talk a little bit about notation. So if these random variables Well, the random variables could be discrete and they could be continuous. And the time indexing could also be discrete or continuous. So throughout the course, we're going to have 4 things to talk about: discrete time, discrete space, discrete time, continuous space, continuous time, discrete space, and continuous, continuous, which is actually a very small part of the course because there's not that much time for that at the end. So the notation here in discrete time is, so it's just a collection of random variables that I'm usually going to call x0, x1 on up, or maybe we start with time 1, whatever. I'm going to use the convention that I hope you've already seen in probability, and that is that a capital letter such as this is a random variable, whereas a lowercase letter is a particular value. And for me, I'm going to really emphasize lowercase by making it kind of curly. So we might talk about the probability that x equals some x. Like I'll try to make it really small, but definitely curly. Okay, so these are all capital letters, and we can talk about the whole collection by putting an xn in brackets and saying that n goes from, excuse me, 0 to infinity. That's an infinity, not readable. Or, because this is going to just get tedious, just brackets with xn. That is there to represent the entire collection. And so this guy is different from me writing this, because this is a single random variable at time n, but with the brackets is the entire collection. Okay, so in continuous time, what did I write? Example. Continuous time. It is customary, although not required, to use letters like N, M, and K, and J and I for discrete things, and letters like T and S, and maybe U and V for continuous things, although it's not required. But the thing I wanted to write is really what's going to come in the next line. So let me do my first line. And that is that obviously I can't list this collection, so I won't have a ... phrase here, but maybe an x sub t, and the t is all, real numbers greater than 0. And similarly to what we just talked about, maybe just xt. But I'm going to do something a little bit different because we're going to be plugging in time steps with other time steps. And I think that it might not always be clear when I'm talking about discrete time or continuous time. So, and if you want, you can write it either way, but this is what I'm going to do. Whenever it's continuous time, I'm not going to use the subscript at all. So that's an x of t. So then it should be really clear that I'm talking about a continuous time process. So we'll have like xn or xt for a discrete random variable and a continuous random variable. Is everybody okay? Only see like 3 of you right now, so but please speak up. By all means, it's fine. I mean, it's encouraged. It's great. Okay. So I'm going to define a Markov process, but only informally. And that's because it's defined in terms of conditional probabilities, and we need to maybe do a little review about conditional probabilities. So let me just informally define a Markov process. It is a stochastic process, so it's a time-indexed collection of random variables, and then it has a certain property known as a Markov property. So I just said I wouldn't use abbreviations right out of the gate, but I don't know. I don't like to come in with pre-prepared slides because I think it's a little too boring, and you need to see that math comes from within, like vomit or something. So a Markov process is a stochastic process, time index collection of random variables with something known as the Markov property that I'm about to define. And we're going to write this down formally eventually, but basically it says, I don't know if you want to see me writing these words out, so I'm just going to say it and not write it down. But if you are given, I'll write a little bit. if you are given the value of a random variable at time n, or time t if it's continuous, and the values of the next variables going forward are completely independent of the past history. So if you imagine like a graph of a Markov process where this is time, and just for the purpose of illustration, I'm just going to do discrete time. There's some sort of random movement. Like let's talk about a simple random walk. A random walk, we will eventually define formally, so it's okay if you're not writing this stuff down. A random walk on the integers is just a process where you're at a point, and at each time step, you either go up one with some probability or go down one with some probability. And there's many variants of this. There's variants where you can stay in place, so you can go from 2 to 2. But let's just say we go up with some probability little p, and we go down, horrible arrows, with some probability 1 minus p. So if you followed this random walk around, this is an example of a Markov process. And that is because at any point in time, let's take this one, if you look at where you are, you can figure out where you go next without looking at the past history. That's the Markov property. You know, you'll be flipping a coin or something. So where you go next depends on where you are and some kind of random input. Again, I will be writing this down formally, but that's basically what a Markov process is. And you've probably heard the words Markov chain, which I'll be using a lot. And chain refers to a discrete time process, although I'm not going to care if you use them wrong. So a process could be discrete or continuous, and a chain is always discrete time. Okay, so given this suggests that we're going to need some conditional probability here. We're actually going to need a lot of it. And so I wanted to review some stuff with you, and then we should be full swing into Markov stuff by Monday. So here is a review of conditional probability. Okay, so the just in case you don't know this at all, I've got a deck of cards. I don't know if you could see my little picture on the top of the screen. It's really not important. And I'm going to get it open eventually. I'm going to randomly select a card. Huh? You weren't supposed to see it. So I hope you didn't see it. But if I asked you what the probability that this card is a king, you would answer 4/52 or 1/13, because there's 4 kings out of a total of 52 cards. It's just counting. And if I looked at this card and said, you know, it's a face card, which means it's a king or a jack or a queen, and I asked you now, what is the probability that it's a king? This is a conditional probability. You're given information. And so you've restricted the whole world down to just 12 cards, 4 kings, 4 queens, and 4 jacks. And out of those, there's 4 kings. So you would say 4 out of 12, or 1/3. That's a conditional probability. And if you were betting here for a king, you'd be so wrong. Yeah. Okay. So Gomer, eat the 4 of clubs. Okay, so let me write that down with events. When you start learning probability, you've got events that are represented by capital letters A and B. And so the conditional probability of A occurring given B is occurring is denoted by the probability of A and then like a horizontal line and then a B. So this is read as given. And this whole thing is defined as the probability that A intersect B happens over the probability that B happens. And I like to always go back to, if I'm having any trouble with rules of probability, to Venn diagrams and thinking of probability as area. So if you look at a Venn diagram, and by the way, today I looked up Venn. His first name was John. He's kind of like Band-Aid or Xerox. Like you don't really think about like it's an actual brand or person. So John Venn, way to go. Okay, so a Venn diagram, it's got some circles representing sets. And in probability, you can think of area as probability. And you can think of the rectangle as the entire sample space of all possible outcomes. And you can think of the rectangle as having area 1. And if you have two events, A and B, and again, think of probability as area, once you are given that B occurs, you are definitely in here. And now you want the probability that A occurs. So I don't know if you could see that, but it's that little intersection there. So you are restricting the universe and you're computing the area. Let me get a better color. All right, same color, but I'll shade it differently. You're computing the probability that you're in here, given that you're in the stripe set. So you're just shrinking your universe. And I bet you already know that, but what a shame it would be to start off this course with people being lost. So I just want to get us on the same page today. And by Monday, we'll be doing stuff that hopefully is new to all of you.
Quick question. Would it be wrong to say it's conditional is a transformation of the sample space?
It would not. That's actually, yeah, we're going to do that, especially when we come to random variables, which is pretty soon. When we talk about the probability that, say, x equals x, given y equals y, it's really the probability that x equals x under some different kind of law. And thinking of it that way is really going to help you use prior concepts or properties of probability and convert them into probabilities in the conditional land, because it's just like transforming to a different space. Yeah. So other questions? As I scroll. Okay, so I know this is one more basic thing, and that is that we define the events. I said one more, I didn't say the last. I know it sounded like we're done with basic, it's just another one. So we define events A and B to be independent if, so I know how you've probably defined them. Well, actually, I know nothing about you yet, but usually this definition is that the probability of the intersection is the product of the probabilities. But we can define it equivalently with conditional probability, which is kind of what I prefer. Because defining it with conditional probabilities, I would say that A and B are independent if the probability that A occurs given that B occurs is just the probability that A occurs. It's saying that B doesn't matter. And you totally get that out of, I mean, these guys are equivalent, because if color, sorry, if this is true, this is saying the probability of A intersect B over the probability of B equals the probability of A. And yeah, there's something to worry about if this probability is 0, but let's just assume it's not. So then you multiply this to the other side and you get the original definition. But I really like that idea of a definition of independence. The probability that A occurs given that B occurs is just the probability that A occurs. It doesn't matter. That sounds independent to me. Multiplication doesn't really sound independent to me. I can't draw multiplication in Venn diagrams. Okay, so we are going to not really be using events, but random variables, and we're going to start off discrete. Maybe you recall, hopefully you recall, that if x is discrete, we can talk about the probability that x equals x. But if x is continuous, the probability that x equals x is always 0, because there's just way too many values. Like the probability the next person you see today that their height is between 62 and 73 inches is decently large, but the probability that their height is between 62 and 62.1 is very small, and it's shrinking, 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 and you're never going to see an exact height. assuming you can measure with infinite accuracy. So we're starting off with discrete, and we're going to be in the discrete regime for quite a while. So let's go. Okay, so conditional probability with random variables, the probability that x equals some x given that y equals some y. So I was too lazy. I should have started by saying let x and y be random variables. So x equals x is just an event. This is like the event A, where A is defined to be the event that I observe x to be little x. So everything is the same. There's nothing really special going on here. This is the probability that x equals x and intersection y equals y. Please come back. This is really, I know this is really basic. I just, again, want us to all start off on the same footing. So it's the same definition as before. And an and in probability is represented by a comma. So we would write this as the probability x equals x, comma, y equals y, over the probability that y equals y. Okay, and so if we have independent random variables, so if x and y are independent, which I'm sure you've seen in your previous probability class, it means that the joint probabilities factor into the two individual or marginal probabilities. Then we have the probability that x equals x given y equals y is just the probability that x equals x. So Markov chains, again, are defined in terms of conditional probabilities. So that's why I'm doing all this right now. And we're probably going to use these conditional probabilities more in the reverse way. So I usually say unraveling. I don't know what I say, but check this out. In the event case, the probability of A given B is the probability of A intersect B over the probability of B. And that's just the definition of conditional probability. But this implies that the probability of A intersect B is the probability of A given B times the probability of B. And I usually refer to this as unraveling conditional probability. You know, you use what you need based on the information you're given in a problem and what you want to know. So I don't know. I don't know if I should make this a formal thing. Unravel definition of conditional probability. We're going to be doing that a lot. And what else do you need to know? A couple more review things. We're going to be using the law of total probability and Bayes' rule a lot, but I don't actually bother to call them that. It's just kind of natural probability calculations to me. So let's just do one example of a conditional probability problem. So I've got 3 boxes. Why boxes? Because I can't draw urns. It's always urns in probability. I've got 3 boxes labeled 1, 2, and 3. Labeled 1, 2, and 3, each containing some red, blue, and green balls. Red, blue. Okay, so here is my box, which I can't even do that well. Box 1, box 2, and box 3. And then let's say box 1 contains 2 red balls, so I'm going to write 2R. And who knows, 3 blue balls and 1 green ball. And let's say the second box contains 2 red, 2 blue, and 3 green. And the third one, let's say 3 red, 1 blue, and 3 green. I know. Please come back. I know it's really basic. It's going to be insane, though. In this course, we're going to get to C infinity. That's right. I will not elaborate on that because that will just be too much of a tangent. Is someone gonna ask something? I thought I heard like a mic unmuting. Okay, so this is, if you're taking notes, you're probably not. This is important to write down because it's not going to make sense when you look at it later, but I'm slow at writing. So here is the experiment. We're going to randomly select a box. So box 1 with probability 1/3, etc. And then we're going to go in there and randomly select a ball. And I want to know the probability that the ball we draw is green. Right? So I'm going to denote the boxes selection by B1, B2, B3, and the event that I get a green ball with a G. And so what is the probability we get a green ball? So in order for you to understand what I'm asking here, it is important for you to know the setup that I blew through. Randomly select a box and then randomly select a ball. Okay, so the probability of getting a green, which I'm going to call G, I can write this as the, you will never write this again or see me write this again because it's all the intermediate steps, but it's the probability I get a green ball and I chose box 1, plus the probability I get a green ball and intersect, I chose box 2, etc. And I can use that unraveling version of intersecting probabilities to write this as the probability I get a green given I chose box 1 times the probability I chose box 1. That's that quote unquote unravel mood. Unravel, what the, that's not the word I wanted. I don't know what it is. Move. Okay, so I already am a little too sloppy here. Let me write this smaller. So this is the probability of drawing a green given you drew from box 1 times the probability you drew from box 1 plus the probability you draw a green, box 2, probability box 2, plus the last one. I didn't leave myself any more space there. That was the whole point of me rewriting it. But we know all of these because we are randomly selecting a box. So each of these probabilities, box 1, box 2, and box 3 is 1/3. And then once you're in a box, you can figure out the probability you draw a green. For example, in the first box, I have 1 green out of a total of 6 balls. So that is 1/6, etc. This is what's known as the law of total probability. And if you want to quote that, that's fine. But I also think it's something you can just do. You know, some people will write law of total probability on a solution in the homework. Some people will just do what we did and write it out. Okay, so just for completeness, this is 1/6 times 1/3 plus 3 out of 7. 3 out of 7 times 1/3 plus 3 out of 7. I said completeness, but that's as far as I'm going. The arithmetic, not so much fun. Okay, so law of total probability. And the other thing that I'm sure you know is Bayes' rule. So Bayes' rule is going to be invoked anytime you have to compute a probability that seems backwards to you. So working on the same example with the green balls and the boxes, suppose I want the probability. So I went through this experiment. I randomly selected a box. I randomly selected a ball, and I observed that it's green. So what's the probability it came from box 2, given that it's green? This just seems backwards, right? I mean, if you were in box 2, it's easy to compute the probability of getting a green ball. But having a green ball, it seems a lot harder to figure out which box it came from. So Bayes' rule is used to flip conditional probabilities when they seem backwards to you, when the other ones are easier to find. But we don't need Bayes. By the way, the S is part of his name, so it's really Bayes' rule. We can just write out the definition here. This is going to be the probability of choosing box 2 and, that's an intersection, sorry, I'm not using random variables here, and a green over the probability of a green. And then I can use on top, I'm going to use that unraveling of conditional probability to write it in the other direction. This is the probability of a green given you are in box 2 times the probability you're in box 2. And then down here, if I know the probability of drawing a green overall, I could just do that, but probably I don't. So this usually is a law of total probability thing, the last thing we wrote up here. And this is going to be the probability of a green given box 1 times the probability of box 1 plus the next one plus the next one. So that's Bayes' rule. I just call it doing conditional probability stuff. I got to work on that spacing. So again, Bayes' rule is for turning around conditional probabilities that seem backwards and not natural to compute. Okay, so let's get back to random variables. And hopefully by the very end here, we'll have the definition of a Markov chain. And please stop me if you need to. Okay, so if you have, suppose you have a couple of random variables and you want the probability, and suppose they're discrete. Everything's discrete for a long time, so I won't keep saying that. You want the probability that x equals x, and for some reason it's easier to drag in another random variable, just like it was in the box example. Wanting the probability of getting a green ball was easier if we knew which box we were coming out of. So you can do the same exact thing. You can drag in another random variable if it's convenient and going to help you solve the problem. And you don't have to write out all these steps. I'm just going to do it our first couple of times. But you can write the joint probability that x equals x and y equals y, and sum out all the values of y, because that's how you get back to a marginal probability. If you saw these joint probabilities in a table, like values of x and values of y, maybe this is 1, 2, 3, and you wanted the probability that x is 1, that consists of this event, and you would sum them up. And that number would be in the margin, which is why I'm calling this a marginal probability. Okay, so doing our same thing, or unraveling of conditional expectation, this is the sum over y of the probability that x equals x given y equals y times the probability that y equals y. And in this course, we're going to go straight to that all the time. We're going to be doing this all the time. And this is called conditioning on y. Like you have to compute this probability, condition on this other thing. So conditioning on y. And we're going to be doing double conditioning and triple conditioning, and there's going to be a lot of random variables and lots of lines everywhere. It's going to be awesome. Okay, please say something if you want to stop me or have any questions. I don't know about the future when Richie is not here. That, I like taking questions in the chat, but it's really interrupts the flow of the lecture if I keep reading the chat box. So I'm not really sure. The best thing to do would be to just speak up. All right, what else we need to know? Double conditioning. Suppose, and this brings us back to what Michael asked earlier about like sort of transforming the space. Suppose I want to compute a conditional probability, and it is somehow easier for me to bring another random variable in. Okay, so suppose I can compute this if I know the value of a third random variable, z. So I won't keep after this class writing these out, all these intermediate steps, but I want to prove how you can get from the beginning to what I'm going to conclude here. And that is, you can say that this is the sum over all, well, maybe I'm going straight to it. Let me not go straight to it. The definition of this conditional probability is the probability of the intersection over the probability of the second one after the line. And maybe it is easier for me to compute that probability on top there by conditioning on a value of a third random variable, z, meaning that I'm going to compute a big fat joint probability and sum over all the z's. And so if I want this probability for x, given that y equals y, I'm going to sort of move things around. On the top here, I'm going to say this is the probability that x equals x given those two things. You can think of that as the event B. B is the event that both y equals y and z equals z times the probability that that happens. This is, again, unraveling the definition of conditional probability, writing an intersection as a conditional times another joint probability. It's actually always called a marginal as long as you've gone down in dimensions. It doesn't have to be one-dimensional to be called a marginal probability. It's just you started with more and you went down to less, and then it's called a marginal probability. Okay, I still have a denominator here. Probability that y equals y. And then one more step. I won't write out the whole thing because this is just, I don't know. I feel a lot of anger from you that I'm doing this review today. So I just kind of want to get through it. I can rewrite this guy as y equals y. Oops, sorry, that's not what I wanted. I can write it as the probability that z equals z given y equals y times the probability that y equals y. And once I do that, that's all in my numerator. I can cancel this with this. So the bottom line, what I was trying to say is if you trace this all the way through, what we have just shown is that the probability that x equals x given y equals y, if you want to condition on a third random variable z, this is the probability that x equals x given y equals y and z equals z times the probability that z equals z given y equals y. I really have to work on my spacing. And this is what Michael brought up before, which is, I think is what he's thinking. This is the last thing I'm going to say, is that this probability is just a probability for x in some constrained space. So this is like the probability that x equals x in some world where y is already fixed. Like I'll put a little subscript here. And then all the previous rules of probability still work out the same way. If I wanted to condition on a z, where it doesn't look like I'm starting with a conditional probability, I would just do this. But everything would be in this y equals y world. I'm not going to write it that way, but that's what's going on in the line above. You know, the given y is always on the right side of the given line, and it just comes along for the ride. So I'm out of time. I promise you that next time will be more interesting. I hope to see you there. This is officially my office hour. It starts at 2:50, but I'm just going to stay. I mean, so if anyone wants to stick around and ask or say anything, please do. But thank you for coming. Welcome to spring and welcome to Markov.
Thanks. And go.